Welcome to the next session in quantum parallelism in machine learning models. So the lecture outline is quantum parallelism in machine learning model and what are the key processes are involved. Next is importance of quantum parallelism in machine learning model and quantum parallelism in reinforcement learning. So what is quantum parallelism? It is a fundamental concept of quantum computing because here we are going to simulate all the process in multiple computational nodes and paths, and we are going to reach that with the help of superposition and entanglement. Here is a structured and explanation of presentation for your understanding. The first core principle is quantum superposition. Qubits exist in states of ket 0, ket 1 or both simultaneously. So both has to be perform their operation in parallel representation. And the next is entanglement effect. Entanglement qubits create exponentially growing the state space. So here n qubits is to be represented as 2 to the power n states. So where operational all kind of this kind of operationals are affects all the states simultaneously. So we have multiple inputs are affect all the states. Next, unitary transformations. Quantum gates manipulate superposition states to perform parallel computation across all represented inputs. So all the inputs are to do their parallel representation. Key process steps. First, we are going to prepare n qubit states in ket 0, tensor product of the power n. Apply Hadamard gates to create superposition of all 2 to the power n states. Execute quantum algorithms via iterative operations, and process affects this kind of process affects all the states simultaneously through quantum interface, amplitude manipulation and entanglement correlation. So everything to be adapted in each state. And what is the next is importance of quantum parallelism in machine learning. Speed up of the computation, so it reducing the training time for ML model. Enhancement of model accuracy, can process large scale of data very efficiently. Efficient optimization improves gradient descent method and optimization in deep learning. Solves high dimensional problem ideal for quantum enhancement in neural networks. So next working principle here is superposition. A qubit exists in multiple states, ket 0 and ket 1 at the same time. Quantum gates apply transformation to process many states simultaneously. Interfaces used to amplify correct correlation solutions, and we can go with a different kind of optimization. And the next is measurement. We can go with the quantum states to yield the final result. For example, if a classical computer computes f of x for a single input, a quantum computer computes f of x for all kind of x input in one single step. So here we have a different kind of approaches for thinking about the quantum speedup in machine learning. ML task here is searching based on that factoring, and next is PCA and optimization. In case of searching, Gruber's searching method is to be implemented. In classical time complexity, we will get as order of n. For quantum time complexity, we can go with the order of root n. In the case of factoring, input factoring methods, we have a different kind of method is called as SHARS. So here the time complexity is exponential and quantum time complexity is polynomial. For a principal component analysis, dimensionality reduction, for classical time complexity order of n square, for quantum time complexity order of log n. And the next is optimization. QAOA method is applied. Here the time complexity is exponential, and for quantum time complexity is polynomial. D-coherence and qubit fragility. Short quantum state lifespan is also to be considered here. Qubits lose superposition due to environmental influences because we may have a different kind of environmental factors out there, like radio waves, vibrations, temperature fluctuations also to be there for computational issues. Next is sensitivity threshold. Maintaining entanglement requires isolation from external noise at levels challenging to achieve with current materials. And the third case, operational durational limit. Most systems sustain coherence for microseconds, restricting algorithm complexity. So these are the major challenges in implementing quantum parallelism in practical application. Correction and complexities. So here error correction also to be considered for all kind of qubit states. The first one is error accumulation. Quantum operations have intersonic errors 1 times of 1000 operations that compound exponentially in large system, and for redundancy requirement, effective error correction may need thousands plus physical qubits per logical qubit, straightening the current hardware capabilities. Fabrication precision, subatomic defects in materials may disturb the qubit's stability during scaling process. And the next is control system complexity. Each added qubit exponentially increase gate and synchronization challenges also. So these are the error correction complexities are to be introduced in qubit calculation. Next is quantum parallelism in reinforcement learning. Parallelized policy updates are also to be used in reinforcement learning, and quantum value iteration also to be introduced. Quantum gradient free optimization also to be introduced. So in the parallelized policy updates, faster decision making is introduced in the complex environment. Quantum value iteration speed up the Bellman equation computation, and quantum gradient free optimization we can go with the high dimensional reinforcement learning problems, and we have a different kind of use cases are also there, and robotics, game, AI, and financial trading. So thank you learners, we will see in the next session.